This class, and especially Friday, we will be ramping up the difficulty, or at least the intimidating factor of some of the calculations we do in class. This is naturally kind of a barrier that calculus experiences. The way that I'm trying to help you all kind of accommodate for that is that we're spacing out the difficult material along with some reminder material, all in the form of helping to go through the story that was the development of calculus. Now, that being said, it doesn't mean that the calculations are any less intimidating. If you know that you're having a little bit of difficulty already keeping up with like some of the ways I'm manipulating equations and variables, you really want to make sure that you're doing everything in your power to set yourself up for success. The number one thing, if you are not printing off and using the guided notes, you need to start doing that. There's going to be some things that I will not be able to cover in depth story-wise that the notes will help you to remember. There's also some things that are going to get intimidating and we're going to go through somewhat quickly for at least some of you. And if you have the guided notes, that gives us a basis where we can go back through it and we can clarify, we can add some topics. You don't have to write down so much. You can focus more on the conversation we're having during class. So this is my reminder that if you're not using the guided notes, you want to be using the guided notes. It's also my reminder that if you are looking at any of the techniques that I do on the board and you're going, no, that's okay, I've got this, just make sure you've got this. The techniques that I'm choosing, especially for factoring, you remember when we used the rectangles and we were doing the area model with the factoring? Some people are still not doing that, as evidence on the quiz. That's okay. I won't take off points if you're using another valid way of getting it. Like, it's all math to me. It's all fine. However, if any part of your work looks like magic or doesn't explain what's in your head on the paper, I can't credit it. Because as a grader, I've got to kind of pretend that you are guiding me as if I don't already know. Also, the reason I've made these techniques is because they protect you against the errors that I see semester after semester. So if you think you've got this, that's okay. Go ahead and do it. If, however, it starts to be a place where you are getting homework questions wrong or you're getting confused and you're not using my techniques, I would strongly recommend you re-explore and consider using my techniques, because to you, this is your first attempt at the material. To me, I have guided thousands of students through calculus, and I know where the common mistakes are. I'm trying to protect you. So if you choose to go off book, that's cool, but then it's you doing you, and I'm no longer responsible for if what your process is goes haywire. Okay? So I'm just trying to remind you all that, like, that's why I'm doing it. It's not because it's weird or new, for the purpose of being weird or new. It's because I'm trying to either protect you on some materials, or I'm trying to help build a story for chapters yet to come that you don't even know are coming yet. So just kind of a reminder, the guided notes cover all of that. So I would recommend that you use the guided notes if you're not already. And if you ever have any questions, feel free to shoot me an email or join for office hours. There's like, what, a total of 12 or 14 hours now available for help every week. And I think the Math Assistance Center, which is 2 floors up, is going to be live and available for even more hours throughout the week. So there's absolutely no excuse for you all to be confused at any point and just beating your head against the wall. If you're confused, come and reach out. We will happily help you, because it's going to ramp. This is my warning. All right, let's go ahead and do a little bit of review here. So we're going to start off with the question of the day. Remember, take this off on a scratch piece of paper if you would. And go ahead and respond to this one. For everybody online, give me a moment. I'm going to go ahead and throw this in as a poll. If I look at the very first one, that is missing a detail. Remember that this is best understood as a story where we're going through it and saying I am compounding growth over and over and over again. That means I'm multiplying over and over and over again. This first statement does not have that. You can put it on the table there. So that first one has no repeated multiplication. It violates the story and how we built it. The second one looks pretty good. We're looking at repeated values because there's an exponent. And I've got that whole idea of getting my money back and then some interest split up for every period. That works out pretty well. The third one, for forever large values of n, this is one that I did give you, but we called it an informal definition, right? Because what is a forever large value of n? Anybody got any takers? It's not a very easy question to answer, right? So that's the barrier of calling this a formal definition. There's no such thing as a forever large n. Right? There's nothing to plug in for that. Similarly, for the last one, speed limit of growth, that's a great conceptual foundation. It is not formal. How do we know it? How do we get to it? How do we know it's the speed limit and upper bound? All of that came from limits. So again, there's going to be times where I'll give you a concept and you should latch onto it. It's a good concept. Hold it. It's going to make it easier to deal with these questions in your mind. But then immediately we've got to start training ourselves to go from the informal to the formal. In the same way as me saying making a forever long list is not making a forever long list. It's imagining making a forever long list. The number at the end of the forever long list. There is no number at the end of forever, but it's a decent idea. So we've got to kind of take these informal ideas and then bring them back to their formality. That's where we're going to be able to work with them and keep them true. It begins with this mathematician, Descartes. Descartes is famous for a quotation, "I think, therefore I am." This quotation came about from René Descartes having essentially a midlife crisis, because Descartes was trying to understand how he could do his formal math, his formal philosophy, and write deep thoughts in his literature, but he came up with a very difficult and profound question. Let's all take a look at, for example, your chair color. What color is the chair? Ish. Maroon, can we agree maroon? Now here's a question for you. How do I know that the maroon I see is the same maroon you see? Said another way, how do you know that I don't see that as your green? But I grew up all my life hearing people call it maroon, so I call it maroon. But it's green in my eyes. Do you see the question? How can you trust your senses against my senses if we can never compare senses? How do I know that the things I have touched that I call hard, you feel as soft, but use the same word? Do you see the difficulty? It's a deep question. Threw René immediately into a midlife crisis, trying to wonder if he could trust anything he's ever thought ever. And that's where this quotation came from. Because one thing he did realize is that he is thinking, right? In order to ask these questions, he would have had to be thinking. In order to be thinking in the first place, he has to exist, and that became the foundation of modern mathematics, modern philosophy, and a good chunk of literature. We're going to start from logic and thought, nothing else. No, I saw it in the real world. No, I touched it with my hands. No, I thought 2 was represented, but no, thoughts only, logic only. Saw it out in the real world, can't be trusted. Very profound idea, very unique, about the 1700s. One thing that René also was known for in these deep thoughts was lying in bed late into the afternoon, as many of you might relate to, right? Thinking profound deep thoughts. One time he was doing this, he's looking up at the ceiling, he notices a spider. Spider is tracking across the ceiling very close to this one, and he wonders to himself, can I determine where that spider came from and where it is going? In other words, can I draw a curve that tracks that spider's path? And if I can figure out what that curve is, can I predict the future? This is a cool idea. It's also one that was very radical, because you've got to remember there were 2 types of mathematicians. There were the geometers that believed in shapes. You analyze it by you drawing it. And then there's the algebraists who play with equations, that anything that works for the equation is considered legit. So they're coming up with numbers that the rest of the world doesn't even believe in, like negatives. Oh my golly, those can't exist. I've never touched them. 0, never touched 0. That must not be a good answer for the geometers either. And God forbid it comes up with an imaginary answer, right? So we've got to start to, like, and all of a sudden René is saying, I wonder if I can make an equation that also draws a path. In other words, also creates a shape. Let's look at an example that helps clarify that. We have here a circle. A circle, if you talk to a small child, is a perfectly round shape. You draw it. There are no X's, there are no Y's, there are no symbols. But René comes up with this idea of making a coordinate plane, where he's going to call the horizontal X, and he's going to call the vertical Y, and give them variables like the algebraists play with. So let's see what we can do. If I draw this circle, the circle from a geometer standpoint is starting at a center and then working its way out along a radius to some point. Well, I see that if I am going out at a diagonal, I can imagine a little grid on top of here, and I see a right triangle. We all see the right triangle? What do we know as the equation that deals with right triangles? Pythagorean theorem, which is a squared plus b squared equals c squared. We're not going to use x's and y's because I haven't figured out how those play in yet. So we get a squared plus b squared equals c squared. Great. In this situation where I have my triangle, do we see that the diagonal is 5? It's the radius. The radius is the same as the hypotenuse. I can make both of those 5. So we can make this r squared if we wanted, or 5 squared. All right, what about A? A is a vertical here. Is that different or the same as Y? What do we think? We think it's different? Let's check. A goes up from the x-axis to the point. Y would go up from the origin to a height. I think it's the same height. So I think in this case, A is Y. Do we all feel all right if I do that? All right, so we'll put that in. Y squared. What about B? B is right here along my triangle. X is a distance away from the origin sideways. So I can make a little side equation. I could say something like X is 2 units and then B. Do we feel good with that? I'm seeing a lot of blank stares. Help me out. Give me a general nod if we're feeling all right. All right, cool. So that means that B is x minus 2. Are we all right with that? So if I want to describe that side of the triangle, I can put that in over here. I can make it x minus 2 instead of B. I can do a little rearranging, and it looks like the circles that we have all explored in algebra class. So in other words, circles are triangles where I go from a center out to a general other point. Now this is wild. If you went and showed this to a small child and you said this is a circle, they would look at you like you have 3 heads. This is not a circle, this is a bunch of symbols on the page. But from the model of logic that Descartes had with the coordinate plane, we can say that this also represents a circle because it's about the logic behind the symbols. All right, any questions on this one before we keep going? Okay. Let's play with some more. I've got an equation here. Y is equal to 3x squared plus 2x minus 2. Who knows what that's going to look like when I graph it? It's going to be a parabola. Okay, excellent. How do we graph the parabola? I know of a lot of ways that algebra books will tell you. I know we can make it into vertex form. We all remember completing the square and making vertex form and having to pull it out of formulas and stuff like that. Yeah, if you don't remember, it's because it's really hard and you probably don't remember it. Like that, it's not common. Factoring maybe and then solving things, but that doesn't really give us the shape. Here's how I like to play with these. What looks intimidating in this formula? The x squared looks intimidating. Can we all agree? Excellent. Let's make it look less intimidating, shall we? If I take this and I make it x times 3x plus 2 minus 2, have I changed the meaning or only changed the appearance? I've got one voice for appearance. What do we feel like? Change the meaning or the appearance? The appearance still means the same thing. Does it look less intimidating now? Like just visually speaking, right? Maybe we don't know what to do with it yet, but maybe visually it looks less intimidating. Here's what I like from here. Let's let creativity drive us. What number is begging to be plugged in here? What number, if we put it in, would have incredibly far-reaching consequences? 0 is a great one, right? Because if I plug in 0, do you see how all this goes away? Let's try that. All right, I'm going to plug in 0. X equals 0. The whole beginning part goes away. I'm left with -2. That's a point. I can go and I can put that in 0, -2. That's right here. Wouldn't it be nice if that parenthesis also had a way of zeroing out and killing it all off in the beginning? Let's figure out what that would be. 3x plus 2. If all that went away, that would go away by, we could subtract 2. Divide by 3. X equals -2/3. So if x is equal to -2/3, that whole parenthesis goes away, becomes 0. cancels a bunch of stuff off. We're left with give me feedback. Where are we at? If this is negative 2/3, the whole parenthesis becomes 0. 0 times x is 0. We're left with if all this goes away, we are left with louder, y'all. I can't hear you. It's a quiet room. I hear -2 loud over here. I heard a whole bunch of mutterings over here. Let's try again. What do we get left with? Thank you so much. All right. So then that means if x is equal to -2/3, the whole beginning part goes away. We are left with -2. Do we all feel good with that? All right. So I'm going to plot that. -2/3 is going to be a really, really skinny thing right there where I go down to a height of 2. Excellent. I heard before this is going to graph as a parabola. Parabola looks like this. Do we all agree? Is it symmetric? Am I going to get the same thing on the right as I get on the left? Same thing on the left as I get on the right of this graph? Yeah, cool. So that means that halfway in between some point of the same height, I should have the vertex. Do we all agree? All right, what's halfway between -2/3 and 0? -1/3. So that means that -1/3, which is right in here, I could say that's going to be the vertex. X is equal to -1/3. How do I figure out the height for x is equal to -1/3? I could plug it in. Let's plug it in over here. All right. 3 times -1/3 squared plus 2 times -1/3 minus 2. 1/3 minus 2/3 minus 2. I think it's going to come out to -2 1/3, right? So that means that it's going to be a little bit in between, right about there, and I've graphed my parabola. This is my favorite way to graph parabolas. It comes from letting your intuition drive it. What's scary? Make it look different. What would be an interesting number? Try it. What would be another interesting number? Try it. Do they say have the same height for symmetry? Great. Halfway between it, we fold it like a book, plot it, and graph. Much, much easier than trying to go through and do completing the square or trying to factor or trying to use all these other formulas. It's naturally driven. All right, any questions on this one before I go on? Okay. Y'all are getting a little quiet on me and a little low energy, so I'm going to need a little bit more feedback because I know it's partially filled room, but you got to give me that feedback so I know if I need to slow down or speed up. All right, a couple things of vocabulary. Let's talk about domain and range. We've heard them before. I'm just going to reiterate them for the purposes here. Domain, all valid x values that we can use with this equation. Range, all reasonable y values that could come out of the equation. These can be challenging questions. Let's take a look at some of them. I like this right here. If I take a look at this equation, y equals 1/x, I like to look at that through a combination of perspectives. I start with it through my favorite shape ever. My favorite shape is rectangles. I love rectangles because I can think of this as an area problem. Y equals 1/x, that's an area of 1 where I'm taking away one side, which is x, and I'm trying to figure out the other side, which is y. In fact, if you want to make it a little bit more consistent, we could put the x and y's on the other sides. That'd be fine. Right? Area divided by width gets me length. Area divided by length gets me width. This is a story, a geometry story. So let's go ahead and take a look at a few different examples. If I make y equal to something really, really big, like 1,000, what does x have to be? What times 1,000 gets me 1? 1/1,000. All right. Let's flip that on its head. What if x is 1,000? What does y have to be? 1/1,000. What if x is equal to 1? Y has to be... I'm going to stare at y'all until I get some louder responses. All right, thank you. All right. So what that means is that I've got a compensation that's happening. Do you see how that's working through the rectangle? One side gets big, it's got to make the other side small so that it comes out at 1. They're both 1, that works out just fine. Let's try it with some more difficult ones. What if I make this side equal to 0? What's the other side have to be? Can't be anything. Very nice, right? Nothing times 0 will produce 1. So that already tells me that this is not going to be a good response. I'll put that in as the domain. The domain looks like any big number will be fine. Any small number will be fine. 0 makes no sense. So the domain is everything except for 0. If we allow ourselves to play with negative sides, then we're just playing within algebra, and that's still fine too, right? I can make one side negative 1,000, the other side would be negative 1 over 1,000. That would be fine too. All right, what about for y? What value can't go there? For the same logic, 0 cannot go there. So that means that for the range, y cannot be equal to 0. So we can look at it through shapes, get an idea. How does this appear in Descartes' coordinate plane? Well, let's play. Same exact equation. If I start with x equals 1, y has to be 1, because it's that same rectangle, right? So I can plot that point, 1, 1. If I make x equal to 10, the other side has to be 10 and 10 would make 100. 1 over 10, right? It's got bigger, the other has to get smaller. So the height's going to go down, the width is going to go out. It's almost like what I'm drawing are a whole bunch of these tiny little rectangles right there. There's a little rectangle whose size is 1. It got really, really wide, but very short. This one here had a width of 1, a height of 1. If I make it skinny, I'll have to make it tall. And in doing so, I can plot that combination. And this is where we get that graph. It's a graph that tracks along how that rectangle morphs and stretches as we try to keep it 1 in the center. Again, if we allow ourselves the ability to say, deal with diagonals, or sorry, deal with negatives, if I make one side negative 2 and the side is 1, what's the other side have to be? Yeah, exactly right, negative half, right? So then that's going to give us a graph like this. Where it's the exact same thing, but now we've made both sides negatives because they have to cancel each other out. So we've got this play all of a sudden between geometry and algebra. We're able to graph it. We're able to look at these as stories. And sometimes it helps if we have the story, we can flip the story on its head. And once the story is on its head, we can ask what's reasonable to expect that comes out of this story in the same way that we were exploring what went in. Let's look at that some more. All right, here we go. This is a story. It says that I'm starting with an x value, I'm going to square it, and then I'm going to add 2. Okay, so let's play around with some things. X equals 10 is going to go through some kind of process where first I make a square, and second I add 2. All right, if I make a square out of 10, that's a 10 by 10 square. How big is it? 100, right? And then if I add 2, I land on 102. We've got that story. All right, so instead of dealing with specifics, let's now play a little bit. If I made a square where it was 2 by 2, would that be a reasonable square? Like, can we imagine that square in our mind? 2 by 2 square. Yeah, feel good at that. And then if I added a little bit more on that, that's going to put me at something. Can we all agree? All right, what if I make it like 1,000 by 1,000 squares? That can be fine? Fraction by fraction square? Negative by negative square? In algebra land, sure, right? Decimal by decimal square? 0 by 0 square? What 0 times 0 is? So that's still fine, right? Still gets an answer on the end of that. It would be an answer that has no size, but that's okay. Is there anything that won't get me an answer from this story? Is there any number you can't multiply by itself? Let's start there. Any number you can't multiply by itself? Let's do a show of thumbs. Thumbs up that there are no problems with multiplying a number by itself? Thumbs down. There's a problem. I found a problem number. What do we think? All right, so I'm seeing no problems. I would agree with that, right? Negative times negative is going to be something my calculator tells me. Decimal times decimal is something my calculator tells me. Fraction times fraction is something my calculator tells me, right? That'd be fine. All those make sense. I can draw them. I can model them. They're numbers. They're great. Anything you cannot add 2 on top of. We all feel pretty good with that? Okay, so then so far, I've been able to take this x value, even if it's not 10 specifically, if it's anything, I can track it through this process, and it's going to land on a very specific y value. Well, we have a title for that. We call those functions. So this is a function. If I can transform how my starting thing looks, but I'm at no point doing anything but morphing it, this is okay. This is good to go. And since we said anything can go in, that means that the domain is all real numbers. Everything on the number line works with this story. Now, here's the harder question. Is there a number that we shouldn't expect to come out of this process? That's harder. Can we all agree? Right? Following things through the story, pretty okay. Asking what could potentially not come about as a result of the story, that's harder. So here's the way we could do that. Let's flip this entire thing on its head. Instead of trying to go through this process, let's go backwards. Let's imagine that I'm starting with a y value. I'm going to undo every single transformation. So if I'm taking this y value and I'm going backwards through this process, what's the first thing I have to undo? I have to undo the what do we think? Here I did square, then plus 2, got an answer. If I'm going backwards, first thing I need to undo is I need to subtract 2 to undo the plus 2, right? So I need to undo this. So I'm taking this, I'm going backwards and undoing the plus 2, and then I'm going to undo the square, right? How do we undo a square? Very good. Some of you said square root quietly, and some of you said plus or minus square root loudly. Good. Plus or minus square root. So let's draw a brand new equation, a brand new function now. It's like y is going backwards through this process. In doing that, we're going to undo some things. Oh, that's going to get confusing which way I'm drawing it. Let's just draw it like this. Y is going through an undoing machine. And the first thing it undoes is the plus 2. It undoes it by subtracting 2. It tries to undo the squaring by doing what again, everybody? A plus or minus square root. So if we track that through, then we should get y minus 2 plus or minus square root should return me to my x. This is what we could call an inverse. Inverse for having flipped the conversation, making it backwards. Yeah, go ahead. Nope, no stupid. What do you got? I like that. That's a good way to have it. Keep that as a back check because it's not only that it can't be negative, there are more things on top of that. You'll see it in a moment, but that's exactly right. You should have an intuition and then we'll verify that with the math. I love that strategy. So let's take a look here. If I was going to look at this as it's written, is there anything you can't subtract 2 from? We feel, give me a shake. Anything I can't subtract 2 from? Okay, we feel pretty good. Any number minus 2, answer at the end of that, right? All right, any number you can't take a square root of. Good. 0 square root I think would be all right. That'd get you 0. Square root of, was it? 5. 5 would still work. It'd get you a decimal, but it would still be a number. Negative numbers, right? Can't square root negatives. Because it's asking, find me 2 identical things that multiply to create. Well, they can't be identical if I came out as a negative. So square rooting negatives doesn't work. That means the inside here can't be negative. Y minus 2 has to be 0 or bigger. Well, that means that y has to be bigger than a 2. Well, there you go. That's our range. Our range is all numbers that start at 2 and go on forever big. So if we double check it with the intuition, you're completely right. Positive numbers should be expected. But on top of that, it's actually all positive numbers only after we get to 2 and beyond. So we have this competing threshold. So it helps if we're able to rearrange the equation and then go through that story mode again. Is it possible? Should I expect? Is that going to work? And we look for the problems. So here are some notations that I'll use as I'm trying to describe the different functions, right? We've got functions. They're a transformative process. X is transforming to look like Y. How is it transforming? Depends on the steps, but it's just transforming. This is the full diagram. This is the definition I will give you for functions. X is being transformed to look like Y. This is the diagram. We're coming back to this again and again and again and again and again. What's an inverse function? An inverse function is this idea of trying to take the destination and backtrack it to its origin. Backtrack it through. But sometimes this is not convenient to write because we start to lose track. Am I supposed to be going left to right, right to left? What's going where? So we'll use this notation here. This notation here means backwards through F one time. Sometimes people will look at that and they'll go, that's an exponent, but that's somebody who's letting their eyes drive the math, not the logic and the story drive the math. Because exponents are repeated multiplication. How do you multiply a machine, a process? That doesn't make any sense. So it's not multiplication. It depends on what the base is. This right here is a story. So I'm trying to undo the story one time. Versus if it was a number, then I'll give it to you. Exponents means repeatedly multiply, so undoing of that would be repeated division, which is why negative exponents are division. But this isn't a number, this is a process. We're undoing it one time. It all depends on the story behind the symbols. All right, let's do a couple of quick fire ones. Let's look for some ideas. Let's start with this one here. Function, not a function, equation, not an equation, inverse, not an inverse. What do we think? Let's get some ideas. Let me see a hand. We'll bounce it around. Please. Function, how come? It gives what? It gives out one answer for each x, right? So let's double check that. It's difficult to see that in the diagram, but I'm not going to change the meaning of this process if I write it like this. That's still true. X1 gets assigned to y. I can track it through this process as it looks at y. That's fine. I can also do it when I'm looking at x2. x2 goes through the same process and comes out looking like y. So maybe this is a process that makes everything look like y. That's fine, right? There's nothing wrong with that. I just need to be able to track it as it goes through. All right, let's compare that to this one. Function, not a function. Equation, not an equation. Neither. Let me see a hand. What do we think? Yeah, please. You keep it up if you can. Talk through it. Talk through the math. But so you said it was a inverse function. How come? Okay, good. I like that. For the inverse part, we've got it going backwards that's occurring, right? Y is getting assigned backwards to an x. I'm on board with the inverse. Talk to me about function. Do I have one thing being transformed to look different? Yeah. So y is being transformed into what? So that's two different things. Is it being transformed to look into one thing? It's two things. So you're completely right on the inverse, but it's not a function. And that's the biggest thing if I can get people to recognize, is that the inverse function has two criteria. One is that it's an inverse. It takes us backwards. And I like that. So it is an inverse. Is it a function? Function would require that I can diagram this like y goes to one and only one thing. I don't have one thing I can put here and capture the same meaning. So it's not a function. It is an inverse. We could call this something like an inverse relation. I can relate it backwards, but it's not a function. There's not a function that's taking me from single start to single finish. Let's try another. Function, inverse function. Inverse equation, equation, relation, neither. What do we think? Let's see another hand. Yeah. Relation, how come? Each input is going to an output. So I do have some relating. So we can almost kind of think of these as like big overarching structure. We've got relations. Relations is any way of relating things. I like that. Below that, we have a specific kind of relations. We call those equations. Equations require an equal sign. Do I have an equal sign here? Anybody see an equal sign? That's not an equation. Is it a function? Functions are specifically when I take one thing to one destination each and every time. Do I have that occurring here? No, specifically with the 2, right? The 2 is being taken to 2 destinations. That violates the diagram. All right, what about this one? Don't worry about the details in the graph. Function, inverse function, equation, inverse equation, relation, neither. What do we think? Let's stare at this side of the room to see if I can get an idea. So let's again kind of adopt Descartes' idea of horizontal is our x, and I'm starting there. If I start at a sideways value, is it going to be clear one and only one vertical value for each? All right, now I see some shaking of heads. So let's get some people shaking their heads. That'll tell me, so what does that mean this is or is not? Not a function, very good, right? If I have a single x value, like this one looks like it's like 85-ish. If I have a single thing, a single x value that has multiple y values, that doesn't work. So it's not a function. We could take function, inverse function, function off of the list. What about inverse? Is this a backwards? Are we doing a backwards at any point here? No, I'm seeing a lot of shaking heads. Okay, so that takes away anything with inverse on it. Do you see an equal sign? I don't see an equal sign either. All right, not an equation, so this could be considered none of that. It could maybe be considered a relation. So a relation is just one way of trying to relate something to other things. That's fine, but it's not a function. And that's what I'm trying to drill in here. Function goes back to that specific diagram. I should be able to track x as it morphs into y. There should be no splitting, no extras, no loss, right? So let's go ahead and do a rapid fire. Let's start off with A, function or not a function? Not a function. Who can tell me why? Let me see a hand. Yes. Oh, I was hoping you'd bring up the vertical line test. Here's the thing about the vertical line test. The vertical line test is not a reason. It's a good test. We'll explain it, but it's not a reason, right? It'd be like me saying like, hey, I went and I got like a COVID test. COVID test says I'm sick, so I'm sick. And I'm like, why are you sick? And you say, because the test made me sick. The test did not make you sick. The test pointed out that you were already sick, right? So the vertical line test doesn't make it not a function. It just calls out that it isn't a function. But why isn't it a function? Go ahead. That's what I like to hear, right? X has multiple y values. It always comes back to this diagram. This is how we have defined a function. If you found a visual way of recognizing that in pictures, have at it. Great, love it, big fan. But if I say, why is it a function or not a function? It comes back to a single x has a single y each and every time. So, all right, that one is not a function. What about B? Function or not a function? Not a function. How come? Somebody else? Same reason, very good. For at least one x value, I have ambiguity in if I've transformed up or down or both or neither. That's not going to help when I go back to making my infinitely long lists, right? It's not a function because x is not being transformed to look like y. C is a function or not a function? All right, so let me hear a little louder from everybody. Function, not a function? Function, you said not a function. What are you feeling?
Not a function.
How come?
Same reason as
So let's check. Let's grab a certain x value like this one right here. And let's see. If I was going to find the y value, do I go down to it, right? Is there going to be one, or is there going to be another one that's further below or further above? It would just be that one. And if you do that for each and every x value, that's going to be the same case. There's going to be one height above it or one height below it. So it's like I've got little miniature transformation machines happening in each of these, right? That x value is going in, it's being transformed to a single y value. So it's always back to that diagram. Good. What about D? Function or not a function? Try again, everybody, a little more energy. It is a function. Very good. Because again, we can check it with a vertical line test, but then when I ask you why, it's because the vertical line test is a way of checking that every x value is transformed into one and only one y value at most. Yeah. C is a function. Yep. Which we can see with the vertical line test, which we can say why the vertical line test, it makes sense with the definition of function. All right, so we've got the vertical line test. I'm okay with the vertical line test. Use the vertical line test. But if I say why, vertical line test is not a why. Vertical line test is just an indicator, not a reason. Okay, make sure we're always going back to that common definition every single time. Horizontal line test. Yeah, I remember being very confused about when I use it and when I don't. Horizontal line test. Here's the way I make sense of it. It's an absolutely inherently worthless test. It does nothing except it tells you about failure yet to come. So let's do an example. I'm going to graph this for you, which is a positive square root graph. It's going to go up a little bit, and it's going to go down a little bit. We already explored that this came about as the inverse for this graph. Now you all tell me, function or not a function? Not a function, right? So if I wanted to invert this, I can invert it to a graph. I can get an inverse graph. I obviously have it. It's right here. I could maybe even have an inverse equation because here's my equation. Here's the inverse equation. Inverting is fine. Does it have an inverse function? Because this is the inverse. Is it a function? Y'all told me a moment ago, is the second graph a function or not a function? Y'all got quiet on me again. Function or not a function? Not a function. So it'd be nice to figure out, does y equals x squared have an inverse function? Well, this would be the result of inversing it. Does it have a function? Not a function. So inverse, but not a function. So if I wanted to predict that after I make this inverted, I do or do not have a function, it's almost like what we're starting with is what you all just did in your mind. You did the vertical line test here, right? What would the vertical line test, this red dot, this line, have looked like on this graph? Was it a little louder? What would the vertical, that red line, what would it look like on the first picture? Not what is it, just what would it have looked like? Horizontal line. Do we all agree that that's how the graph would have transformed and the that red line would have transformed? It would have flipped. So the horizontal line test tells you nothing except that after you invert it, you won't have a function. That's the horizontal line test. The horizontal line test is just a way of predicting that you're going to fail the vertical line test after you invert it. So it goes, inverting is flipping the story or the graph. That's fine. Function means I transform singularly, 1x to 1y. Inverse function means that I have flipped something and it transforms singularly. This one here was able to flip. It did not have a function at the end of that flipping. We could have predicted that with the horizontal line test. So the horizontal line test is nothing but the vertical line test one step backwards. It's not its own thing. In my mind, I don't even worry about it. I just imagine the vertical line test and then the idea of flipping. Keeps it all nice and simple for me. All right, let's talk about some transformations. I'm going to see, make sure I don't go a little over here. All right, a couple of different things. I really hate rules in this class. This is my reminder again, I hate rules. If it doesn't make sense, it's not worth doing, and we're all kind of spinning our wheels and wasting our time. So how many of us have heard that this right here has a center at 2 because I see a 2 with my eyes? General show of hands. Have we all heard that rule? Yeah, I hate that rule because here's the thing that my algebra students have difficulty with. But it says minus here. And I'm like, I feel that. Anybody else remember having that where it was like sometimes it's a minus and I shifted it one way, sometimes it's a minus and I shifted another way. I can't remember which way does which or anything. I'm going to clarify it all for you right here, right now. If I was going to label x somewhere on my coordinate plane, where is x? It wouldn't be the vertical, horizontal. If I was going to label the y would be the vertical. Very good. If I look at this equation, does anybody here see circle minus 2 or do we see x minus 2? X minus 2. So I'm not taking the circle and shifting it, I'm shifting the x values. I'm dragging the crosshairs out from underneath the graph. Because if we had started with x squared plus y squared equals 4, that would have graphed as a nice circle right here with radius 2. And then it's like I take those crosshairs and I drag them. I drag them in what direction? Towards the negative. How many? 2, because that's what I literally see right here. X minus 2. Take it, shift it to the sideways towards the negative 2 times. That's going to take this and shift it. It's going to take this and shift it as I move those crosshairs towards the negative. It's going to make the circle look like it drifted behind to the positive. That's why it ends up there. It's not because I moved the circle, it's because I dragged the x-axis. So if I wanted to shift this up, I would take the axes and I would pull them down. Next time, we're going to start getting into how do we cooperate between algebra and the shapes to be able to find the size of curved regions. It's a lot of math. Get prepared. I'll see you on Friday.